Welcome back to the CADSIM Plus tutorial series. My name is Renaud, Manager Mineral Processing at Oral Systems. Please review Part A for setting up the stream chemistry used in this video. In Part B, the thickener will be set up to concentrate or thicken the solids to a default % solid slurry concentration at the thickener underflow, and to also specify the fraction of total incoming mass flow of solids that report to the underflow. Since we now have a pipe or process stream containing a defined flow, we can add the thickener part. Alright, so to add a thickener, select the Insert Part tool in the toolbar to open the Insert Parts dialog box. Find the Thickener.par part by going into the working directory and following the path My CADSIM, Parts, Process, Mineral. In the Minerals folder, you will find the new components to be used for building minerals processing simulations. Select the Thickener.par part and click Insert. Position the thickener to the end of the first process line drawn and click OK. Enter the desired name for the part. In this case, we will call it CCD1 and then click OK. The current default module for the thickener consists of two polygons, namely a mixer polygon and a separator polygon. The names for each of the polygons are given in grayed out fonts belonging to layer 101, which is made invisible during simulation mode. The mixer polygon takes on the role of the feed well, where effective mixing of the incoming slurry with flocculants and dilution streams occurs before evenly distributing the flocculated feed over the entire settling area of the thickener. The separator polygon will split its components, in this case water and hematite, among its outlet streams according to their phase type. As you can see, the thickener already comes with a local spec at the underflow that is predefined. Clicking on this local spec followed by the Edit button reveals the free variable water in kilograms per second is specified with a direct setting equating the suspended solid conc with units % at the underflow to a constant of 20. This sets the anticipated slurry underflow concentration to a suspended solids percentage of 20. The thickener part will require the user to specify the last free variable, which are the solids in the stream chemistry. To do this, click on the Specify and Run Simulation button. Click Yes to save. The dialog box now asks to specify the free variable Fe2O3 solid, which happens to be the first and currently only solids in our lists of components. This time we select the local specification icon or spec and select linear equation in the equation type drop-down menu before clicking on the Place button. Since we expect most of the solids to report to the underflow of a thickener, we place the local spec on the process line on the bottom of the thickener. Subsequently, the specification dialog box gives the option to add a term by clicking on Add Term. This allows us to equate the Fe2O3 solid's free variable to another term in the drawing. Place the Add Term spec on the process line linking the mixer to the separator units. In the new dialog box, equate Fe2O3 at the separator outlet to Fe2O3 at the mixer outlet from the drop-down menu, and multiply the latter by 0.7 before clicking Finish. This will equate the mass flow of solids at the thickener underflow to a fraction of 0.7 of the total solids entering the thickener. Click Yes to save the drawing and enter simulation mode. Click the Run button on the toolbar and observe the green light in the Convergence button. Now feel free to observe the flows in the process streams by selecting any line or polygon. As you will note, during steady state, the thickener outlet will have a suspended solid concentration of 20% as well as a total suspended solid flow rate of 7 kilograms per second, indeed equivalent to the specified fraction of 0.7 of the incoming solids in the defined stream chemistry. Clicking on the solid specification also reveals the calculated value of 7 kilograms per second for the solid's flow rate. Another equally valid method to specify the solid mass fraction reporting to the underflow can be done as follows. Let's return to the draw mode, select the solid's free variable spec, and click Replace. From the equation type drop-down menu, select Split Percentage and click Place, and then place the spec back on the underflow process line. In the new dialog box, enter 70 as the amount in percent of the inlet solid mass flow that will report to the underflow. Click Finish. Again, enter simulation mode and observe the underflow stream variables. Click on the newly replaced spec, this time allowing us to edit the percent of solids at the underflow during simulation mode. This time, to visually observe the effects of changing the fraction of the total solids reporting to the underflow on the suspended solid concentration at the overflow, we can add a chart. Select the Create Strip Chart button at the toolbar and select the overflow outlet stream. Pick suspended solid concentration, click Accept, and note the value of 4% solid concentration in the chart. Now observe the dilution of solids in the overflow on the chart as the underflow solids fraction is increased from 70% to 98%, all the while maintaining the 20% suspended solid concentration at the underflow specified initially by the local specification to left of the underflow line. I hope this tutorial was helpful in showing you how to specify and create a simple simulation involving a slurry passing through our thickener minerals processing unit. Please leave us a comment or email us for any questions or requests for future tutorials.